All right, welcome back to the deep dive. Today we're diving into something pretty fascinating at that intersection of machine learning and automotive engineering.
Yeah, absolutely.
We've got a paper that explores using, well, the power of LLMs
Oh, okay.
to automate the creation of domain-specific meta models.
Interesting.
Now you might be thinking, meta what?
You're right, metamodels.
Yeah. So if you're designing or developing any kind of complex system,
Mm-hmm.
especially like in the automotive world, these meta models, well, they're kind of fundamental.
Yeah, for sure.
Think of them as like the essential DNA defining all the core concepts and relationships.
Yeah, makes sense.
Like how the sensors in a car communicate with the braking system, for instance.
Yeah, exactly. These metamodels are really the foundation of model-driven engineering, particularly in automotive.
Right.
They're all about making sure everyone involved in the development process is on the same page.
Right.
From different engineering teams to software architects, everyone working with a shared understanding and using a consistent language. Now, as you can imagine, vehicles today are incredibly complex.
Oh, absolutely.
And with this huge shift towards centralized, software-defined architectures in the industry, these foundational blueprints,
Yeah.
they're always evolving. Traditionally, keeping these metamodels up to date has been a very manual and frankly time-consuming process, requiring a lot of expertise. And every time these core models change, it's like a ripple effect.
Yeah, I bet.
It requires updates to countless downstream models and tools. And that's where this paper comes in.
Right.
It dives into a potential solution. It explores leveraging the capabilities of large language models, or LLMs, to automate the construction and updating of these critical meta models.
That's right. The central idea here is to use the natural language understanding and summarization capabilities of advanced LLMs, like, you know, the incredibly powerful GPT-4o,
Yeah.
to generate these E-core meta models.
Okay.
Directly from the natural language requirements that automotive engineers work with every day. The researchers even built a prototype, like a web service, using Python just to demonstrate this. And they use PlantUML for visualization,
I see.
which, you know, makes it easier for people to review and provide feedback.
Yeah.
What really struck me is the potential for, like, massive gains in speed and agility.
Oh, yeah.
Imagine being able to adapt your foundational models so much faster
Wow.
as new automotive technologies emerge. That's a big deal.
Yeah, no, it is a very compelling idea. The paper we're looking at today is LLM-based Iterative Approach to Metamodeling in Automotive.
Oh.
It came out just this past March, and it really lays out the entire methodology and the results of their initial experiments. Their workflow begins with an automotive engineer providing a set of requirements,
Got it.
maybe describing, say, the functionality of a new type of sensor. Then they use something called Retrieval Augmented Generation, or RAG.
RAG.
Yeah. Think of RAG as a way for the system to zero in on the most relevant parts of those requirements. Maybe just the sections on sensors or actuators before passing that information on to the LLM.
I see.
Then the LLM gets to work constructing a partial E-core meta model. Now, if we go back to the blueprints analogy,
Right.
E-core is like a standardized language for those blueprints.
Okay.
It ensures everyone's using the same symbols and structure.
Yeah.
But it doesn't stop there. They also generate an updated model parser.
Wow.
What I think is really clever is the iterative aspect of this process.
Okay, yeah.
The system visualizes the partial meta model as a PlantUML diagram.
So it's not just a one-shot deal.
Exactly. And that lets domain experts provide feedback. Through several rounds, they refine and expand the meta model, ultimately getting a complete and comprehensive one.
Yeah.
And, they also address concerns around data sensitivity in the automotive world. They actually considered how this would work with LLMs that are deployed locally,
Okay.
within a company's own systems.
All right, so let's dive a bit deeper into the paper itself. The introduction really sets the scene well.
Yeah, it does.
They talk about how the shift towards centralized electronic architectures in the automotive industry is really challenging the traditional engineering tools.
Yeah, that's true.
They point out that model-driven engineering and the use of meta models are already pretty common.
Right.
Giving an example of like how SysML can be used on top of the AutoSAR standard. But then they get to the main pain point.
Oh, yeah.
Manually updating these meta models is costly and time-consuming, and it requires a very specific skill set.
Absolutely, yeah.
And that's where the potential of LLMs really comes in.
Yeah.
The authors note that LLMs are already very good at summarizing text and abstracting concepts. And some earlier research even suggests that these abilities could be great for metamodeling.
I see.
So it's not just about saving a bit of time.
Right.
It's about enabling greater agility and accelerating the pace of innovation in automotive.
Yeah, totally. And the
Yeah.
paper's very clear about its goal. Investigating how effectively GPT-4o can automate the creation of these meta models directly from those OEM requirements, through that iterative refinement process. They specifically talk about their choice of the Eclipse Modeling Framework, or EMF, and its eCore meta model language, which are pretty standard in model-driven engineering.
Yeah, makes sense.
They also use PlantUML for visualization, and the fact that they actually built a prototype, that Python-based web service, that really shows the practical focus of this research. So they're not just theorizing here, they're actually trying to build something that works.
So let's break down how the system actually works.
Okay.
The paper has a really good diagram, figure 1.
Right.
It illustrates the entire workflow. It all starts with those requirements from the engineer,
Yeah.
which are then processed using that ORAG technique to really focus the analysis.
Right.
The LLM then generates a partial eCore meta model and creates an updated model parser.
And this is where that visualization step using PlantUML comes in.
Exactly. And that's crucial for getting human feedback
Right.
and doing that iterative refinement.
Absolutely.
But wait, there's more. The authors also talk about how this meta model can be used to create model instances in the XMI format.
Okay.
These are like concrete examples based on the blueprint.
Makes sense.
They can even generate OCL rules for consistency and code for simulators like SAR-RLA.
Wow. So it's really showing those downstream benefits of this approach.
Totally. And the prompts they use to guide the LLM are pretty interesting. For generating the eCore meta model, the initial prompt is really straightforward.
Yeah. What is it?
You are generating eCore meta model without additional comments.
Huh. So simple.
And then the user prompt is equally direct.
What's that one?
Based on description requirements, update eCore meta model, current meta model.
Wow, that's impressive. They can get so much done with such concise instructions.
It really shows how sophisticated models like GPT-4o are.
Yeah, definitely.
The PlantUML visualization prompts follow a similar pattern, basically focusing on creating a class diagram that accurately represents the vehicle components and their relationships.
Right.
Oh, and they specifically mention using the PlantWeb Python library to automatically turn those PlantUML descriptions into PNG images.
Oh, that's a nice touch.
Yeah, it shows the attention to usability.
So they're thinking about the whole picture.
Now, to illustrate this, the paper walks us through a 3-iteration experiment.
Okay.
The first iteration involves sensor requirements.
Mm-hmm.
The LLM, impressively, identifies them as vehicle components and even differentiates sensor types with parameters and inheritance.
Wow, that's pretty good.
Then in the second iteration, they add actuator and power management requirements.
Yeah.
And the meta model grows to include these. The third iteration really highlights the human feedback loop.
Okay, tell me about that.
Based on expert input, they incorporate hardware accelerators into the meta model with attributes like processing unit clock speed and architecture time.
Interesting.
And get this, the final meta model even includes default attribute values taken directly from the OEM requirements.
So the LLM's able to pull out those specific details.
Exactly. Now, the paper also presents performance data in Table 2, covering the 3 iterations with GPT-4o.
Okay.
It shows the number of requirements, tokens used, and the execution time for each.
Makes sense.
As you might expect, the token consumption and processing time go up as the meta model gets more complex.
Yeah.
But here's the key takeaway. The speed of these meta model updates is incredible compared to manual methods.
Like how much faster are we talking?
The researchers estimate a reduction from minutes or potentially even days, for big changes, down to mere seconds.
Wow, that's huge. That could completely change the game in terms of efficiency.
Right. Imagine how much faster development could move. And it's not just about GPT-4o.
Oh, right. They looked at other options too.
They explored using a smaller model called DeepSeek 7b.
Okay.
It couldn't generate eCore meta models directly, but it did manage to create PlantUML diagrams.
Interesting.
So they thought, okay, what if we add a transformation script?
I see, to convert the PlantUML to eCore.
Exactly.
Oh.
Table 3 summarizes the comparison.
And how did it do?
DeepSeek 7b could identify main classes and compositional relationships,
Okay.
but it struggled with more nuanced stuff, like subclass generalizations and attributes, compared to GPT-4o.
I see.
The authors suggest that human feedback to correct those intermediary results from the smaller models could be really helpful.
Yeah, that makes sense. So what's the overall takeaway from the paper?
Well, they basically demonstrated a proof of concept for automated iterative metamodel generation based on text input.
And specifically for the automotive domain.
Right. They also highlight the potential for things like automated software generation and better consistency checking.
Those are some pretty big implications.
Yeah, and they emphasize that larger models like GPT-4o are ready to go now. But using smaller, locally hosted models will require more work. And they outline some future research directions, like handling very large metamodels, dealing with LLM hallucinations, those inaccuracies in the output.
Right.
And how to automatically refine those generated metamodels.
So lots to explore.
Oh, and they also talk about fine-tuning local LLMs on those OVM-specific requirements, but, keeping in mind those non-disclosure concerns.
Yeah, that's crucial for the automotive industry.
And they also want to automate the evaluation of those LLM-generated metamodels.
Makes sense. You want to make sure they're high quality.
To fully grasp the impact of this, let's step back and look at how metamodels are usually created in the automotive world.
Okay, yeah.
Model-driven engineering has been around for ages.
Right.
But creating and maintaining metamodels has largely been a manual process, often relying on a few experts.
Yeah, definitely.
Now, with the rise of LLMs, we can apply AI to more abstract tasks, like knowledge representation and reasoning.
So this research is applying cutting-edge AI to traditional engineering practices.
Exactly. It's a natural progression and potentially a really transformative one.
Yeah, the key innovation here isn't just about using an LLM. It's about automating a task that's always been labor-intensive and required special expertise.
Right.
And they're using readily available and increasingly powerful LLM technology to do it. That iterative approach, combined with the PlantUML feedback loop, is smart.
Yeah, it really incorporates that human expertise.
And the fact that they're looking at both cloud-based and local deployment shows they understand the practical side of things in the automotive industry.
Yeah, like data security.
Exactly. And the initial results with GPT-4o are very promising. They suggest a big jump in both speed and accuracy in capturing those complex domain relationships from requirements.
And the challenges with the smaller model also give us valuable insights.
Right. It's about balancing those trade-offs between computational resources, model accuracy, and needing extra techniques.
So what real-world impact could this have if it keeps developing?
Well, for those in automotive, imagine much faster adaptation of software architectures to new trends.
Yeah, that'd be huge.
And the cost and time of maintaining those models could go down dramatically, freeing up engineers for more innovative work.
Right.
It could also empower engineers to evolve their domain models more easily.
Yeah, I like that.
Ultimately leading to faster innovation in vehicle design and functionality.
And by exploring local LLMs, they're addressing those data privacy issues.
Absolutely.
Which could lead to wider adoption by OEMs.
Right. It makes it more practical for them.
This leads us to our novel notion segment.
Ah, yes. Time to think outside the box.
Building on this iterative metamodeling, let's imagine a future where the metamodel isn't just updated in steps, but evolves continuously.
Okay, so like in real time alongside software development.
Exactly. As engineers work on the system, maybe creating instances or trying out deviations for prototyping, a continuously running LLM is monitoring everything. And it would propose very specific updates or refinements to the metamodel in real time based on what it sees.
So it's like a living, breathing document that adapts to the implementation.
Precisely. So what kind of research could support this?
Well, it builds on the iterative approach in this paper.
Okay.
And relies heavily on the LLM's ability to understand changes in the text descriptions.
Right.
We can look at principles like continuous integration and continuous deployment from software engineering for inspiration. And research on anomaly detection in model-driven development could help us figure out how to interpret those deviations from the meta model.
Yeah, makes sense. So what kind of impact could this have?
We could end up with super agile meta models that perfectly reflect the complexity of modern vehicles.
So they wouldn't become outdated or restrict development as the system changes.
Exactly.
What about some less obvious implications?
Well, it could really blur the lines between meta model design and implementation. We might see new roles emerge, like AI-assisted metamodel curators.
Yeah.
People working with domain experts to guide and validate that AI-driven evolution.
So that collaboration between human intuition and AI would be key.
Absolutely.
So how likely is this to become a reality?
I'd say it's a moderate probability. The biggest hurdle is figuring out how to validate those LLM proposed changes automatically.
Yeah, you don't want the core blueprints changing without proper checks.
Exactly. But as LLMs get better at reasoning and we get better at managing their output, this dynamic approach to metamodeling becomes more and more likely.
It's definitely an exciting area to keep an eye on. So this research really shows the potential of combining LLMs with established engineering methods.
Yeah, we're just scratching the surface of what's possible.
And for those who want to dive into the details, we'll link to the paper in the show notes.
It's a great look at the future of machine learning in the automotive industry.
And it really makes you think about how AI will shape not just how we build software, but how we define the very foundations of engineering.
That's something to ponder for sure.
Thanks for joining us on The Deep Dive.